Hello and welcome to this presentation related to the torsion of circular sections, for example shafts. Within this presentation we'll consider the theory behind the simple torsion equation, also known as the simple torsion formula. Note that I use the terms equation and formula interchangeably within this presentation, as both terms are used in various reference sources. We will consider solid circular sections subject to an applied torque, and also hollow circular sections subject to an applied torque. Here's a brief presentation overview related to the simple torsion theory for circular sections. We commence with a brief introduction to the topic area. We review the underpinning assumptions of the theory. We then consider the derivation of the simple torsion equation or simple torsion formula, what's termed part 1, shown here. Then we continue the derivation for part 2, shown here. We then have a comparison between simple torsion and simple bending theory and the formulae derived. We refer to this formula, m upon I equals stress upon y is equal to E upon R from our previous bending presentation, and we show the analogy between the various terms in simple torsion theory and simple bending theory. We then consider the polar second moment of area for solid shafts. We prove the formula J is equal to pi d to the 4 upon 32, and also the polar second moment of area for the hollow section shaft. The hollow section J is shown here. Finally, we show the proof for transmission of power. Power is equal to torque multiplied by angular velocity, P is equal to T omega, and an equation we will use quite extensively in the next presentation where we apply simple torsion theory to various practical problems. And here are the approximate timings related to the commencement of the various sections within the presentation, hopefully to aid your ease of access through the presentation. But please note these are only approximate timings. Introduction. This presentation considers both solid and hollow circular section components that are subject to torsion. Specifically, the stresses and strains in members of circular cross-section bars subjected to twisting couples or torques, denoted as capital T and capital T dash, shown in figure 1, here and here, will be considered. These twisting couples have a common magnitude T, but are in opposite senses. In other words, T is shown in a clockwise sense here, and T dash is shown in an anti-clockwise sense here. These couples are vector quantities, so can be represented by either curved arrows, as shown in figure 1a, or by couple vectors using the right-hand screw rule, shown in figure 1b. Here's the right-hand screw rule depicting the sense of the couple. Let's consider some engineering applications. The most common application is provided by transmission of shafts, which are used to transmit power from one location to another location. Typical examples can relate to a steam turbine connected to an electric generator, from an electric motor connected to a machine tool, or from an engine to the rear axle of an automobile. There are further examples I'm sure you're aware of. These shafts may be either solid, as shown in figure 1 on the previous slide, or they may be hollow, as shown in figure 2 here. Here's our hollow section. Outside diameter capital D, inside diameter lowercase d. So applications continued. Considering a system consisting of 3 component parts, that is turbine A, generator B, both connected by transmission shaft labelled AB in the figure 3A here. So here's the turbine labelled A, the generator labelled B, and the turbine and the generator are connected by the transmission shaft running from A to B. Notice the rotation omega of the shaft. Analysing these as 3 separate parts, as shown in figure 3b here, it is seen that the turbine exerts a twisting couple, or torque, T on the shaft, and that the shaft exerts an equal torque T on the generator. So the turbine exerts torque T on the shaft. Notice the direction of torque T is the same direction as omega, angular velocity, and the shaft exerts torque T on the generator. And the generator reacts by exerting an equal and opposite torque T dash on the shaft, and the shaft by exerting the torque T dash on the turbine. These are required for the equilibrium condition. So here's the reactive torque T dash from the generator on the shaft, and here's the reactive torque T dash from the shaft on the turbine. Let's consider some of the assumptions made within simple torsion theory. As with all theories applied, there are usually some underpinning assumptions that we need to be aware of, and for simple torsion these are outlined here. So assumption 1, the material is assumed homogeneous and isotropic. From our previous presentation on elastic constants, we know isotropic materials have the same elastic properties in all directions. Homogeneous materials have the same composition throughout the body. Thus a material that is homogeneous and isotropic has the same elastic properties everywhere within the body. Assumption 2, the material is assumed elastic and it obeys Hooke's law with the shear stress, Greek symbol tau, considered proportional to the shear strain, Greek symbol gamma. In other words, our shear modulus or rigidity modulus, G, is equal to the shear stress divided by the shear strain. Assumption 3, induced shear stresses do not exceed the material's elastic limit, where this is clearly defined, or the limit of proportionality. Assumption 4, the shafts considered is straight, having a uniform cross-section along the entire length considered. Assumption 5, the applied torque is constant along the length under consideration. Assumption 6, cross-sections which are plane before twisting, two-dimensional in other words, they remain plane during the twisting. Assumption 7, all cross-sections rotate as if rigid, in other words, every diameter rotates through the same angle. And assumption 8, the twist is small and uniform along the entire length of the shaft. So let's consider the proof for simple torsion theory. Nothing clever here from my perspective. This is a standard proof shown in most textbooks. I'm just going to try and illustrate it as simply as I can, showing you the steps involved with generating the simple torsion equation, which we'll use in the next presentation, where we'll analyse various shafts in bars, etc., subject to pure torsion. So let's consider a shaft of length L, sketch here, having an outside radius of capital R here, and being subjected to an applied torque capital T, shown here. The resulting angle of twist, denoted as theta, shown here at the end of line AB, here's line AB, A to B, becomes helical line AB dash, shown here, A to B dash. An angle theta, again shown here, is subtended or enclosed by arc length S, and arc length S is shown here on the sketch, S. So considering shear strain, symbol gamma, shown here, that would be defined as the arc length S divided by the original length L. Or that could be written the lengths of B to B dash divided by the length AB, shown on the diagram. From our previous work related to radian measure, arc length denoted B to B dash is equal to the outside radius R multiplied by angle theta. So we could write shear strain gamma as R multiplied by theta, or divided by the length of the shaft L. I've called that equation 1 purely for reference. Here's our proof continued. Now shear or rigidity modulus, symbol capital G, can be written as the shear stress, tau, divided by the shear strain, gamma. Call that equation 2. Rearranging equation 2, shear stress is equal to the shear modulus multiplied by gamma. Call that equation 3. If we now substitute equation 1, derived on the previous slide but shown here for convenience, into equation 3, then the shear stress is equal to G multiplied by R theta upon L. Call that equation 4. If we now rearrange equation 4 by dividing both sides by R, we have shear stress divided by R is equal to G multiplied by theta divided by L. Equation 5. If we now change the capital R here for the outside radius to any radius, denoted as lowercase r, we derive the equation of shear stress divided by R on the left hand side of the equation is equal to G theta by L on the right hand side of the equation. And this forms the first part of our simple bending formula. Just call that equation 6 for reference. Proof of our torsion equation continued. So hence, for the assumed inner concentric tubes, shown here in figure 4, the relative movement between the ends of the shaft, we denoted that as gamma on this slide here, will be less than at the outside surface. So if we consider one small concentric tube of area delta A shown here, positioned at radius R shown here, then rearranging equation 6 on the previous slide, we can show that shear stress is equal to G theta multiplied by lowercase r divided by L. Equation 7. Figure 4 here shows the distribution of shear stress in a solid cross-circular section. So for an external torque applied, capital T, there is an internal resistance generated by these various small concentric tubes each generating a small force, denoted as delta F here for this tube. And that force divided by the cross-sectional area of this thin ring, denoted with a thickness of delta R, generates the internal shear stress. And this shear stress on the right-hand diagram shows the value 0 at the center of the shaft, where the radius is 0. So in equation 7, for a value of R of 0, shear stress is 0. And how the shear stress varies linearly, increasing to a maximum shear stress, tau max. So that's the distribution of shear stress across the solid circular section being twisted. Proof continued. So let's now consider the torsional shear stress on our inner concentric tube. That's this value shown here on our sketch. So the shear stress is equal to the force, delta F, shown here, divided by the cross-sectional area, delta A, shown here. Just note, for a very thin-walled circular section, the area is 2 pi r multiplied by delta r, where delta r in this case is very small compared to the actual radius of the tube. So the force, delta F, across the transverse plane can be calculated from the formula delta F is equal to the shear stress on our tube multiplied by the cross-sectional area. Call that equation 8 for reference. If we now substitute equation 7, derived on the previous slide but shown here for reference, into equation 8 above, then the delta F is equal to g theta r divided by L, that's from equation 7 here, multiplied by the delta A. Called that equation 9. Now, as the moment, or the torque, is generated by a force multiplied by a distance, where the distance in this instance is the radius of the tube from the center of rotation, then we can state our torque delta T from our concentric tube as g theta r upon L multiplied by delta A, and now multiplied by the radius r. Call that equation 10. Simplifying, delta T can be written as g theta upon L, now multiplied by r squared, multiplied by delta A. Call that equation 11 for reference. And just notice the r squared here is due to the r multiplied by r in equation 10 here. So r multiplied by r is r squared. Our proof continued. So hence summating, or in mathematical terms integrating, all the delta T's for all of the concentric tubes within our section, we find the resisting torque, capital T, is a summation of equation 11 shown here on our previous slide. Call this summation equation 12. However, we know that the values of shear modulus G, angle theta, and the length of the shaft are all constant for all concentric tubes. That relates back to our assumptions made in our theory. So therefore the equation 12 above for the resisting torque can be written as g theta upon L outside of our summation or integral sign, and inside the sign we have the r squared A terms. Call that equation 13. So as we assume the force acts tangentially for each of the inner concentric tubes, then the effect of the force multiplied by the radius is a pure turning moment, a pure couple, or a pure torque. So the moment of resistance is the total of all the turning moments, and for equilibrium these must equal to the applied torque T. Now the quantity summation of r squared delta A from our previous slide, this quantity here in equation 13, is given a name, and it's known as the second polar moment of area, generally denoted by symbol capital J for circular sections. And J has the SI unit of meters to the 4. Also, sometimes we use millimeters to the 4. So therefore, we can now write equation 13 on our previous slide, this equation here for torque, as T is equal to G theta upon L multiplied by the second polar moment of area, capital J. Equation 14 here. If we now rearrange the equation by dividing both sides by J, we form the equation T upon J is equal to G theta upon L. It's equation 15 here. If we now equate equations 6 from our previous slide, but shown here for convenience, the equation 15 shown above, we produce what's often termed the simple torsion equation, based on our simple torsion theory applied here. So the full equation is torque T divided by second polar moment of area J is equal to G, the modulus of rigidity, multiplied by theta, the angle of twist, divided by the length of the shaft, and that's equal to the shear stress at a particular radius within our cross section. So T upon J is equal to G theta upon L is equal to tau upon R is the full simple torsion equation, labelled as equation 16 here. Let's consider hollow section shafts. Now figure 5 below illustrates the shear stress distribution induced within a circular hollow section shaft when subjected to an external torque, again capital T. On consideration of the shear stress distribution, it's seen that the maximum shear stress still occurs at the outside surface of the circular cross section, and now there is a minimum, note it's not zero, shear stress at the bore of the shaft. So using the same analysis as in the previous part of the presentation, we have an externally applied torque T, and that's reacted by the internal resistance of each of the concentric tubes, each applying a little bit of force, delta F, at their radius location R. So note the shear stress distribution is still maximum at the outside surface of the shaft, but for a hollow section it actually has a value at the particular inside radius, lowercase r. So this is the shape of the shear stress distribution across a hollow circular section. Here's our proof continued. So it should be noted that the simple torsion formula shown within equation 16 on the previous slide is applicable to both the solid and hollow section shafts. The difference in section is accounted for by the polar second moment of area calculation, J. And just note for reference 1, the angle of twist, theta, varies directly with the length L. That refers back to this diagram here. So the longer the length L, the larger the angle of twist theta. And item 2 here, as the shear stress is equal to TR divided by J, then for an applied torque T, the shear stress is proportional to the radius, lowercase r. So shear stress proportional to r. Hence the maximum shear stress occurs at the outside surface and decreases to 0 at the centre of a solid circular section. So based on this proportionality, these relationships shown here apply. Let's now consider a comparison of the simple torsion equation or formula with that of the simple bending formula. Usually when I'm delivering the torsion lecture, I have previously already delivered my simple bending lecture. And I like to draw an analogy between the two equations or the two formulae that have been derived. So let's consider simple torsion and simple bending formulae. So we'll compare them and see that certain terms are analogous to each other. So here's our simple torsion formula. T upon J is equal to tau upon R is equal to G theta upon L. And here's a nomenclature related to the formula. It's important to note for reference that the angle of twist theta is actually in radians. We use radians in the derivation, so theta must be in radians in the torsion formula. And sometimes the quantity theta divided by L, angle of twist divided by length of the shaft, is termed the torsional stiffness. And notice for reference also what's termed the elastic polar section modulus, denoted as ZP, is equal to J divided by R, where R tends to be the maximum radius, because when we're undertaking calculations, we're usually considering the maximum shear stress, and that relates to the minimum elastic polar section modulus. And also for reference, I've included the conversion from radians to degrees, as I'm sure we know by now, but I've stated it here for completeness. Our comparison continued here. This is now the simple bending formula we reviewed in a previous presentation. The M upon I is equal to the stress upon Y is equal to the E upon R, or in this case the M is the maximum applied bending moment, Newton meters. I is the second moment of area about the neutral axis, meters to the 4. The lowercase sigma is the maximum bending stress, newtons per meter squared. Y is the distance from the neutral axis to the fibre under stress. In meters, usually it's the maximum fibre, maximum distance. R is the radius of curvature, meters. And E is the elastic modulus, or the Young's modulus, newtons per meter squared. We also have EI, which is sometimes termed the bending or flexural stiffness. And again Z, which is the I divided by the Y, which is termed the elastic section modulus. As our comparison continued, just stated both formulae here for reference, torsion and bending formulae. So what we notice first of all is that torque T in our simple torsion formula is analogous to bending moment M in our bending equation. Shear stress tau in our torque equation is analogous to the bending stress sigma in our bending equation. The shear or rigidity modulus, capital G, torsion equation, is analogous to the elastic or Young's modulus, simple E, in our bending equation. The radius R, in our torsion equation, is analogous to distance Y, in the bending equation. Length L, in the torsion equation, is analogous to the radius of curvature R, in the bending equation. And the torsional constant J, more commonly referred to as the polar second moment of area, shown here, is analogous to the second moment of area I, shown here. So some similarities between the equations, and essentially if you understand how to manipulate the simple bending formula to rearrange at various quantities, then you'll understand how to manipulate the simple torsion formula. We'll look at application of the simple torsion formula in the next presentation. Let's consider the polar second moment of area calculations. So this is the calculation of the polar second moment of area J for a solid section shaft about its longitudinal axis. So to calculate the polar second moment of area about O, shown in our diagram here, for a solid circular section, shown in figure 6. And also noting that the area delta A, shown here, of our concentric tube here, located at radius r and having very thin thickness delta r, can be written as 2 pi r delta r. So to calculate the value of J for this section, we basically have to work out the area of the ring and multiply that by its radius squared. So the integral here, which summates all the concentric tubes or rings, is the r squared multiplied by the delta A above. Just noting that 2 pi is a constant, so it can be taken outside the integral. Simplifying inside the integral, we've got an r squared multiplied by an r, so that's an r cubed. And we're integrating with respect to r here. That's a standard integral of the form ax to the n we've reviewed in a previous presentation. So r cubed integrated with respect to r becomes r to the 4 upon 4. If we now impose the limits of d upon 2, that's the outside radius, and 0, that's the centre of the shaft, we derive a formula for the polar second moment of area of a solid shaft as pi d to the 4 divided by 32. That's a very standard formula you'll find in any textbook or reference book related to torsion's theory of circular section shafts. And just notice for reference that the polar elastic section modulus, denoted as Zp, would be pi d cubed divided by 16. In other words, dividing by d upon 2 for the outside radius. Just note for reference, here's the equation for J above, but stated on 2 lines. Call that equation 17 for reference. And similarly, for a circular hollow section, having an outside diameter of capital D, shown here, and an inside diameter of lowercase d, shown here, we can again calculate the polar second moment of area about point O, the centre of the shaft here, using a very similar process as that showed for the solid section shaft on the previous slide. So I'll let you review the solution here at your own pace. Just notice again that the upper limit is the outside diameter divided by 2, but this time the lower limit is not 0, but the inside diameter divided by 2. Imposing the limits on the integral, we find that the second polar moment of area J for a hollow section shaft is pi multiplied by the outside diameter raised to the power of 4 minus the inside diameter raised to the power of 4, all divided by 32. The equation for J is stated here on 2 lines and labelled equation 18 for reference. Let's consider transmission of power by constantly applied torque to a shaft. So a torque, capital T, is applied to a rotating shaft of radius r, as shown in the sketch on the right hand side here. Here's the radius r, and here's the torque applied. Notice the torque applied is generated by the force F, shown here, on the applied to the periphery of the shaft at radius r. So the torque is equal to force multiplied by radius. The shaft turns through angle theta, measured in radians, and that's in time t seconds. Thus the angular velocity of the shaft, lowercase omega, is theta divided by t, and that's in radians per second. Transmission of power by a constant torque applied, continued here. So let's consider the work done by the force F when moving through angle theta. Remember from our previous presentation related to an introduction to work done, that work done is the product of the force multiplied by the distance s moved in the direction of the force due to the force's point of application. So in other words, work done W is force multiplied by distance. Sometimes we use the term displacement. And work has a unit of the Newton meter or joule. From our previous work on radian measure, arc length S, shown here in our sketch, is equal to radius r multiplied by angle theta. So now we can write work done as the force multiplied by r multiplied by theta. But from our sketch, torque T, shown here, is the force multiplied by the radius. So in other words, work done can be written as T multiplied by theta. But now power is defined as the rate at which work is done. So P is equal to work done divided by the time taken. That would have the unit of Newton meter per second or joule per second. So power can be written as the torque T multiplied by angle theta divided by the time taken. But we know from our previous slide that omega is equal to theta divided by time. So we can write the power equation as the torque multiplied by the angular velocity. And although the derived unit is actually the Newton meter per second or the joule per second, we designate the Newton meter per second as the watt. So there's a small proof outlining how the formula P is equal to T omega can be derived. And this will be a useful formula when solving problems related to the torsion of circular shafts. Here's the bibliography used to help generate this presentation. Some very good textbooks listed here. I remember well using some of these textbooks on my technician engineering studies and also on my degree studies, as well as a more recent textbook. So I hope this presentation has been of interest to you, and I look forward to seeing you in part 2 when we then apply the simple torsion theory we've overviewed in this presentation to solve practical engineering problems. Thank you for viewing.